Excellent. Good morning, everyone. That's very exciting summit. I think this nice hub and seas conference is quite fun. I think that's one of those conferences when you talk about poo and urine, everyone seems fine to name them. You know, my son loves to attend these conferences because every time this name comes up, he's so much, happy actually. I will bring him next time because we refer to it number one, number two, blah, blah, but this is quite fun. Anyway, so in this project, we are looking at extracting some stuff from urine and replacing the cement, basically, that we use in construction in very short term. You might have heard about BioBreak, but we are utilizing it for more add value for infrastructure and so on. So my CIs, Professor Hadi Khabaz, who is here, also our PhD student, Niti, who has been working tirelessly last a year and a half and so, and our industry partners. So it's just I present on their behalf. So I will skip this. So in this particular project, we are looking at improving the infrastructure built on top of closed landfills. So as you know, because of the continuous urbanization, increasing population, and so on, a lot of lands that we need to build our infrastructure are not that great. And many projects, particularly, for example, in Sydney, I know it's same in Melbourne, many parts of roads and railway lines may need to cross the old landfills, which are not suitable grounds for built infrastructure because they are very weak and they settle over a long time. That's why you get a lot of cracks on the roads, or they close the railway lines every some time for maintenance. And these two projects are two in Sydney. One is a road project and a spaghetti junction sort of thing you see, and the other one in western part of Sydney, which is a railway project built on landfill, part of it. One of the techniques used to stabilize these grounds and making it more suitable for construction is addition of cement. So in Australia, cement generally is cheaper than lime. In Europe, lime is also very popular. So basically, they mix the cement with the material or inject it in the ground and basically improve it. So which has got, I'm sure everyone knows that the generation of or creation of cement is one of the biggest producers of CO2 emission, which counts for 8% of the world carbon dioxide emission. So there is a great basically incentive there to find alternatives to replace the cement, basically. So the idea of the project is that, for example, for landfills, so what we will do is that we get the urine, we mix it with some stuff. I will show you the formula of that. And then basically you generate the cement in situ. So therefore the ground becomes stronger. Same concept, of course, in a lower level applies to BioBreak to make the break out of clay. So this has been explored. So in terms of the formulation, how it works, this process, we call it biocementation, not artificially cementation, but bioproducts. So you get the urine using a urease enzyme that some bacteria in the soil basically create this enzyme. Then this catalyzes and then basically separates ammonia and bicarbonate. And then we add a separate calcium source. And then this basically precipitates inside the soil as the, calcium carbonate, which is a natural cement. That's why many rocks, of course, are much stronger than soil because over time they have been naturally cemented, right? So that's why we are very much familiar with it. So in simple form, so you will get the urine that has urea, for example, which is the main part of our work, with a lot of water, which is urine, with urease enzyme because of the bacteria. You create bicarbonate, we add calcium, we create calcium carbonate. Still ammonia and ammonium, of course, will be generated, which is some sort of issues for us. So, and then the reason we add this calcium chloride is that one is that we need a calcium source, of course, to create the cement, and the other one is that we need to maintain high pH to prevent the urolithic activity to lose the urea that we need. So the test we are doing, I will show some results, is on the landfill waste. We will compare it with cement and lime and this new treatment, and we do a bunch of tests that generally they are mechanical tests. So we do, of course, some other chemical tests and so on, but we want to see how much stronger is it, how fast water flows through it, and so on. So the initial test that we have done is that we have collected the actual landfill material from a site here near in Sydney. Of course, it's a very big job to collect the actual landfill material, which is composed of, this is a composition of it, composed of wood, 19%. You have got fibrous material like clothes and so on, plastic, paper, glass, soil, and gravel. So fair bit of it is soil and gravel, as you can see, but it's a lot of other materials in the landfill we have. And this is not a municipal landfill. This particular one is an uncontrolled landfill, which are quite a number of them around Sydney, but they are not municipal. So it's fair bit of apparently construction waste and so on went there. So the idea of the project is that we will do this work in 2 steps. So in the first one, which is the stimulation stage. So what we are doing there is that we will grow the population of bacteria, existing bacteria in the soil. So we are, or in the landfill. So we are not adding extra bacteria or microbes or so. Whatever is there, we feed them. So they will grow in population. That's what we need. And the food that you see here is a yeast extract and this first column, basically. And urea is part of that. In the second stage, while the population of bacteria has increased, now we will add this calcium source through calcium chloride. And now with the existence of bacteria, so it will generate that cement that I just showed you in the previous stage. So that's what we are doing. So we have experimented this. This is a setup we have done in the lab. Niti has been working on that for long. We did quite a number of experimentation, but this one seems the most optimal one. So basically we have a suction on top. So what you see here, and then we get the, the suction is on top. So we inject the material from the base, that solution of the yeast plus urea and so on, and then we collect it from top. So we have got an inflow and outflow, and then we just treat the sample here in this cylinder that you can see. It's a compacted landfill that I think I showed you in this slide. This material that is right on the very right is inside this chamber. So this is the first stage, stimulation. Then we add calcium source plus urea and so on, and we treat it. So therefore the material here now has gone through 2 steps and is stabilized. So now we have done the test. First step is to make sure the bacteria has grown enough inside the sample. So the way we do it is that we get a hydrolyze of the urea that is out of the outflow. So, and as we can see, basically the initial hydrolyzing keeps increasing, means the bacteria is active. So that's good. So this is 4 cycles of running this liquid through. Then after that, the treatment cycle starts. So injection of calcium plus urea and so on. And then after we do that, so here we have measured the shear wave velocity of the compacted treated landfill. And as you can see from cycle 0, means without treatment, to 14 cycles of improvement, the stiffness of the soil or compacted landfill has increased from nearly, let's say, 50 to 300, 6 times increase, which is magnificent. So you stabilize the ground and increase the strength of it 6 times, nearly. Then that was this first test is a non-invasive test. So means we don't crush it to measure it. That gives a stiffness indication. Then we do a triaxial test. that basically same as crushing the concrete. We put it in a chamber, we put the air pressure there, then you crush it. This is called triaxial test. It's a very rather, established test in civil engineering. Then here we have done 2 tests. So these are very recent one. Actually, the NITI has presented, given me this one last a few days, we got them actually. So here shows the strengths of the material, a stress and a strain relationship for the untreated and treated with this new, like biocementation. Again, for around 15% of a strain, what you can see is that the strength that we report here is around 200, less than 200. And after treatment, the strength is 400. Potentially, this means, not potentially, what it shows is that the strength of the material, the actual strength, not the stiffness, is twice. This means the size of your foundation is half. So imagine, in addition to the use of cement, how much you can save in terms of casting concrete and so on for the foundation. So obviously, so the benefits that this project has, so what we have seen is that we can reduce the use of general purpose or Portland cement for construction. That has got a good motivation there, I guess, for everyone to use it, reduce the carbon footprint. Therefore, some of the developing or underdeveloped countries, particularly Pacific Island, that they don't have cement, they don't have that choice of using cement even. Therefore, this is what they have, urine, and so therefore they can use. And of course, this will also improve the environmental image of construction industry, which is not that, green. It addresses fair bit of sustainable development goals. I don't think I will go through them. We can look at them. So which is quite exciting, and a few opportunities for collaboration. One is that if we can find other stimulation solutions or enzymes to basically create this enzyme, adding enzyme or other stimulation solutions. Something I proposed last time, last year, was anyone who can help to concentrate urea out of urine. We are so much interested to collaborate with you because we need that urea. Something else that just came to my mind listening is that because we add a calcium source as well, again, if some sort of calcium can be produced through this urine, doesn't have to be very pure, that we can add. Again, we don't have to add extra calcium from other sources. So we are exploring other avenues, obviously, for tailings, paths, and other sort of materials for improvement, other construction materials such as brick, concrete, and so on. And of course, we can also look at using this for the soil moisture retention for agricultural purposes, but I don't think we will have time to cover it during the life of this NICE hub, maybe post-NICE. So thank you very much. That was a brief summary of what we have achieved so far. Thank you.